If any topic in physics claims to be ubiquitous across all the disciplines of physics, I think no other topic can have as much claim as does the topic of oscillation. It is so ubiquitous that there are quotes from physicists that essentially says that all physics is just learning about simple harmonic motion in different contexts. And oscillation is our topic today. Oscillation is what we are going to concentrate on, and hopefully in the series of videos on oscillations I will be able to cover this topic in grave detail, where I intend to meet the needs of students across many disciplines. So here we go. The phenomenon of oscillation in physics is motivated by a special kind of force which is called the restoring force. And in general, this restoring force, F r of x, is named so because it wants to restore the particle to its original position. Now, restoring force is a complicated function of displacement, and assuming there is an equilibrium position, the job of the restoring force, as we have just mentioned, is to act in such a way so that the net displacement goes away. In general, the restoring force contains all the higher order derivatives. Therefore, it can be expanded in a Taylor series. So we can write the restoring force as follows. It has a constant contribution and then displacement times the derivative, first derivative evaluated at the equilibrium position, where the displacement is 0, so therefore x equal to 0, plus x squared divided by 2 factorial, and then, this is going to be total derivative, and then the second order derivative evaluated at the equilibrium position, and so forth.
Now at this stage, I'd like to focus on the fact that this constant term, constant contribution, F naught, must be 0, because if we take x naught to be the equilibrium position, then F naught, which is a constant term, would imply that there is a constant force acting on the object, and that object with a constant force cannot come back to its original position. So a constant force cannot be a part of the restoring force.
We are particularly interested in discussing physical cases where the displacement is sufficiently small. And when the displacement is sufficiently small, we call those cases as the cases of small oscillation. Small oscillation. And this is where we are particularly interested at. In that case, apart from the first term, all the other higher order derivatives can be ignored, And therefore we can rewrite this as fr of x equal to minus kx, where we have defined k to be the negative derivative, first order derivative of the force. And this is the restoring force in the first order, so it always tends to bring the object back to its equilibrium position, and therefore F is always negative, and therefore K is always positive. And this law is called Hooke's law. One of the cases where this Hooke's law can be ubiquitously used is the case of elastic deformation. So as we know, if an object needs to be deformed in such a way so that the elasticity condition is held, then of course that deformation, the magnitude of that deformation must be very, very small. Otherwise, we'll see a permanent deformation and it cannot go back to its previous form. Despite this being a small class of problem, we still have many cases in our life where we see the application of Hooke's law. This is also called the linear oscillation, but in general nature is overwhelmed with the cases of nonlinear oscillations, and we'll be dealing with that in the later part of the discussion.